Hi, this is Eric Riney from Webster University coming at you again with another marketing analytics procedure. In today's tutorial, we'll be discussing forecasting demand using S-curve. Let's get started. All right, to start off, what we're going to do is just really quickly go through an explanation of the S-curve. S-curve is a measure or a way for us to estimate the diffusion of innovation. And if you remember, what that is a theory that explains how information, technology, knowledge gets diffused across a population or across a social system, right? So it's the spread. And if you remember, what happens is with anything, think about new technology. You have a few people who try it out. They're called our innovators. And then it may be picked up by our early adapters. And that's a little bit larger percentage of the population. So we see that now that there's some growth in terms of the number of people that have learned about whatever this thing is. And then we get into the mass of the population, which is our early majority. And as we reach this point right here called our inflection point, we've reached that halfway point of the number of people in the population that could learn about whatever this is or buy this new product. At that point, even though the market will still grow, it's going to grow at a decelerating rate because there's fewer and fewer people who could learn about the product. All right. And so this S curve reflects that aggregate growth in terms of the market. All right. So we start off really low. We begin to accelerate. At some point, the acceleration is going to slow down. We're still growing, but at a slower and slower pace till we reach that upper limit, whatever that upper limit is. Now, on this y-axis, we have it in percent, and it says market share percent. So this is 100%. You can't go more than 100%. But this could actually be a number. I mean, we could say 1 million. Maybe there's 1 million people in the market. And so that's what we use as our number. It could be actual revenue or, it could be number of businesses or something like that. Whatever it is we're measuring in terms of this market, we can use that as our upper limit. All right, so we have two different types of curves that we're going to talk about. One is the Pearl curve and one is the Gompertz curve. The Pearl curve uses what's called a logistical or a logistic function to measure this diffusion of growth or diffusion of information. And the way this works is that it does this symmetrically about the inflection. All right, so we expect that the part of acceleration is going to be mirrored on the other side in terms of the deceleration. All right, to whatever that upper limit is. The Gompertz uses a sigmoid function. You see it's similar. I mean, they both function the same way in terms of, accelerating and decelerating. But this one does not assume that the acceleration is going to be similar or the same as the deceleration. So these two may not necessarily equal each other. All right, so let's hop into the Pearl equation and take a look at it and see how this actually functions. So the Pearl curve equation is L divided by 1 plus A times this exponential to the negative B times the number of periods. Wow, that is a lot. That's a mouthful there. So let's break this down. L is our upper limit. And if you remember, that's what we want to approach. We want to approach some upper limit here. And that's what L is going to represent, that upper limit for us. All right. We have in our denominator this A, which is going to be our rate of change. All right. An exponential Euler function this E function. And this is a function that has been used in finance and other mathematical equations. And it approaches, as n approaches infinity, we expect the number to approach this 2.718 to 81. It goes on and on and on. It's kind of like pi. But it's a very useful function. They use it in terms of compound interest and things like that. All right, B is a measure of our deceleration in growth. All right, so let's really look at this function and figure out what's going on here, and that'll help you understand how Pearl curve works. So L again is in our numerator. It's the upper limit. And if you think about it, anything in our denominator, the impact it has on our numerator depends on the size of the number in the denominator. So if I were to take L, and here I just have an arbitrary number of 100. So if we take L and we divide it by 1, then it's 100. If we take L and divide it by 2, it's 50. And if we did this again, you could see that as the denominator gets, let's try it this way. As the denominator gets larger, then our answer, I'll say, the impact it has on L is that our number gets smaller. All right. So if I were to just do these periods here instead of doing it the way I did here, like this, you can see how this number is getting smaller and smaller and smaller. All right. So basically, as the denominator gets larger, our answer is going to be smaller. All right. But what we want, remember in this, we want this to approach the limit. In other words, we want to, as we go further and further out, we want to move towards 100, not move away from 100. So what's happening here is that this L divided by 1 plus this part of the equation, what's happening in this part of the equation is that this is a number that is going to impact 1, right? 1 plus this, but it's going to do so at a decelerate. First it's going to accelerate, then decelerate. So it's going to start at a large number and get smaller and smaller and smaller. And then that's going to have less of an impact on 1, which is going to have less of an impact on L. So let's just quickly look at this first part of the equation so you can see what's happening here. So this negative and this is B, and you can see here I actually labeled this B times the number of periods. Let's try that again because it didn't work. So I have this minus B. Let's wait. Let's go back because I did something. There we go. So let's try this again. We have equals minus B. And then what we're doing is we are going to multiply that times the number of periods. All right. And you see B is 5. So this is just going to be negative, 0.5. So this is going to be negative 0.5. And as we go further and further out, you see that there is an equal difference in the distance of each one of these. We're, just taking away 0.5. So we go from negative 0.5 to negative 1 to negative 1.5 and so forth. All right. Now what's going to happen, this is getting larger. And if you remember, an exponential number that's negative has what it does to the base is it makes the base smaller. Now, this Euler's function is a logarithmic function, and it in many ways does this type of acceleration deceleration and I'll leave it at that. So we're going to do this exp. So there's actually an Excel equation for this Euler's function, and put this number in, and I'm going to copy this on down. So there we have it. And now you can see that even though this first part is zero point 0.5 for each one of these, this next part is actually doing, it's changing these numbers at a different rate. So the difference between 1 and 2 is not the same as the difference between 2 and 3 and 3 and 4 and so forth. So you see that now this number is getting smaller a lot faster. And that's what we expect to happen here, right? That this, we want the impact of this on 1 to decrease the farther out we go. And you see that happening. All right. And then we're going to multiply that times our acceleration. All right. So, or our steepness, I'll say. And here it's this a times this part of the function, and I'm going to copy this on down. All right, and again you could see that we started at a large number and we're getting to a relatively small number, and we're going to add this. Now we have our entire denominator once we add this to 1. All right, so you see the further out we go, the closer to 1 we get, and that means the closer to the limit we're getting. And you can see how this was 15, 9, 6, 4, bunch of 2s, a bunch of 1s, and then it's really, really getting closer to 1. All right, so now we can see the impact that this has on L. So here, remember our limit is 100, we're at 6, and we can see that, you know, we move up and we accelerate in here, then we start decelerating, and we really, really, really slow down as we begin to reach 100. And that gives you an understanding of how this Pearl curve equation is working. All right. So let's really quickly look at an example of the Pearl curve. I'm going to delete this. I have this in here because I worked it earlier, but let's just start over and put this in here so you can see exactly how it works. All right, so I'm just going to put in, we start with arbitrary numbers, and I like to start with 1, so I have all 1s, and so I'm just going to put this in. And this data right here, let me go back right quick. This data is just, you know, a program. So let's assume that this is a new program that we have at Webster University. And we have, well, it's not new now, but it was new back in 2003. And this is our enrollment information. And so we want to see, you know, what's going on and what can we expect moving forward. All right. So we're going to use this S-curve, this Pearl curve, to estimate what's happening in our market, in our demand. So we go equals L, and you see this is L underscore PEX. That just stands for Pearl example. And I can't use L. I can't call this number L because I'm already using L on this in this workbook. All right, so divided by 1 plus this A function, or this A number, I'll say, exp, and then negative B times our period. And we're in period 1 here. All right. And then I'm just going to copy this down, and I'm actually going to go past the point of the periods that I actually have because I'm forecasting this out. All right, and if you remember with any analytical procedure, basically what we want to happen is that we want to find some model, some equation, and the right numbers in that equation, some model that helps us to estimate what actually happens so that we can use it to anticipate what will happen in the future. Well, the only way we can do that is if our model is accurate. So we need to test it against what actually happened. So what we're going to do to test to see if our model is accurate is that we are going to measure it against actual data. And we could do this in several ways. We could do an R squared variable, we could do a p-value, and in this case, I'm doing a sum of squared error. And sum of error squared just looks at our actual, or I'm sorry, our estimate minus the actual, and we're going to square that. All right. And what we want to happen is we want this number to be extremely small. The smaller this number is, the closer our estimate is to what actually happened. And I'm going to copy this down, and I don't have to copy this all the way down because past the point of having data, there's nothing to compare it to. All right. So I'm summing this sum of errors here, and what I want to do is minimize this. So I want solver to find the numbers that will make this forecast match what actually happened, such that the sum of squared errors will be very close to zero. All right, so let's go into solver. And again, I worked through this to make sure it works. So I already have this in here, but we are going to look at our total SSE. We want to minimize that by changing these three numbers, and we're using our GRG nonlinear. I hit OK, and you can see it really quickly came back, and we compare what we forecasted to what we got. It is very darn close, almost right on the mark. I mean, if you round, it is pretty much on the mark. All right, so our total sum of squared errors is extremely small. That means we are pretty darn accurate. And you can see here, this is my actual forecast. I could, if I wanted to, put in the enrollment data, but it would fit nicely on top of this. So we can anticipate then that, in terms of this program, we are starting to flatten out. All right. We've had our growth spurt, and for the foreseeable future, we're going to be around 710 students, per year. And this is good information to know because, as you begin to reach maturity in some products, it'll be time to introduce new products so that those can go through, or you need to figure out how you can possibly find new markets for this. Maybe this is an on-ground offering and you move it to online, and then you can have another growth spurt. Or maybe if this is a product that you sell domestically, maybe you move it into a foreign location so that you can begin this curve all over again in that foreign location. So this is very useful information. The other part that's good to know on here that I didn't go through when I was explaining the Pearl curve is this inflection point. This inflection point is the point at which the acceleration begins to slow down or decelerate. It's still going, but it's going at a slower and slower pace. All right. So where is that point? It's good to know when that point is happening. Have you reached that point, or are you still accelerating at an exponential function? So here you can see it was around, the first quarter of the 6th year. So sometime in the year 2008, we reached that inflection point and we began to slow down. All right. And now we're leveling off. All right. So that's your Pearl curve. Oh, and to calculate this Pearl curve, let me go back. I'm sorry. To calculate this inflection point, it's the log of A divided by B. So that's how you would do it. All right, so really quickly, let's talk about the Gompertz curve. And this is the equation for the Gompertz curve. I'm not going to go all through what I did before, but you can see the equation is set up a little bit different. It's an exponential Euler function on top of an exponential Euler function. And honestly, I don't understand everything that it does, so I won't even try to explain it all to you. Just know that it works. All right, so let's look at this same data and let's do the Gompertz curve and see how that works. So equals A, and then it's times this exp negative c times exp minus this b times r periods, and then I'm going to take this all the way down, and let's make sure the years are correct right there. All right, and we're going to do our sum of differences again. Let's make sure we square that, and we'll just take this down to here. Okay, and our total sum of squared errors looks like it's calculating the right information. And now we can hop in solver and do the same thing. In this case, we're again minimizing sum of errors, and we're changing these numbers. Before we had L, A, and B, and now we're using A, B, and C, and that's only because that's the letters that the Gompertz curve use. I mean, you could still use L, A, B. It's arbitrary for the most part. All right. Anyway, let's hit solve. Okay. And you'll see here that we actually have a little bit different estimation. All right. For our Pearl, our upper limit was 711. This one says our upper limit is 741. So a little bit different. I mean, not too far off from each other. And it says our inflection point actually happened in year 5. So if you remember going back to this measure, this one tries to create a symmetrical curve. All right, so it's pushed the point of inflection out a little bit. And this one doesn't necessarily do that with the Gompertz. So this one is saying, hey, you accelerated pretty fast and then you slowed down a lot over the past, I'll say, 14, 15 years. And that's how this one operates. All right. So if we were to, let's go ahead and plot this really quickly. All right, there we go. And then let's add in our actual, or that's our actual. Let's go in and add in our forecast. All right, so the blue line is our actual, and then our red line is our forecast, and you can see that it's pretty much on top of our actual, and that's a good sign. So it looks like we have a pretty accurate understanding. Now, if you remember correctly, the Pearl kind of leveled off a lot more here, while it looks like the Gompertz has gone up a little bit, but it's still leveling off. It's going to level off, remember, at 741. That's our upper limit. All right. So there you have both the Pearl and the Gompertz. Really great for estimating demand of the overall market, or maybe your market share, or what's going on with a particular product or something like that. Again, my name is Eric Riney from Webster University. You can contact me at my email information. You can also contact me on Twitter or LinkedIn, and certainly you can find me on YouTube. Join me for another one of my marketing analytics videos. There are more to come, and if you like this one, hit the like button, and you can also join my page. Take care, and I'll see you soon.